Hello, this is John from. This is a tutorial on recursion in Java. Several people have asked me to make a tutorial on recursion, and at first I didn't want to because it's sort of an algorithm rather than, in a way, being anything to do with Java as such. But then I reflected and I realized that in fact recursion is considered something basic that all programmers are supposed to learn. So if you're learning Java, you want to learn recursion along with it. So let's take a look at it here. I've got a main method set up in my application Eclipse here. And let's just put a sysout in there to check that it works. And I'll run this and it says hello. Now I'll define another method here. I'm going to make this other method also static. I might as well make it private because I'm only going to call it from within this class in main. I'll say private static void. And I'll call it, let's just call it for the moment calculate, like this. Now, the reason I made this static, static has nothing implicitly to do with recursion. It's just that I haven't got an object of this app class, and I just want to use a method here directly from within main. And if you want to call a method of a class, then it needs to be static. So rather than do new app and then say app.calculate or something, I'm going to just make this method static here, and we've covered that before, of course. So I can call calculate from within main, of course. Let's put calculate in there and sysout hello and run that, and this is all completely standard ordinary Java. Now supposing I pass a value to calculate, like let's say here, int value equals 4, let's put 4, and then I'll make calculate take an int value and I'll display the value here and I'll pass it in here. Let's run that and check that it works. It says 4. It's important to realise, for the purposes of this tutorial especially, that whatever we do to int value within these brackets will not affect its value here. This is, because this is a primitive type, it's like we're sloshing the value 4 from this variable here into this variable here, which only has the scope of these two brackets here. So if I say something like value equals value -1 or something like that, and then I run this, yeah, it'll be 3 within this method, but down here it's still going to be 4. So let's run that. That's an important thing to grasp. Now as far as recursion goes, we can do something kind of interesting here, which is we can make this method call itself. That's what recursion is. It's where you call a method recursively, or to put it another way, a subroutine calls a subroutine. So here I could say, let's have the sysout in there actually, put value. I can now call calculate like that again. And there's no real actually need to have this in an int here. I can just put it literally there. I just did that to show that it wasn't changed. When we change it within the function, it's not changed within this method. So we can call calculate and let's pass value to it. So the method is now calling itself recursively, and this code is actually problematic. And if we run it, what will happen is we'll get an error. And let's see if I can scroll to the top of this error. It's going to be here somewhere, and there it was, and it says stack overflow error. And what this is when you call a method from within another method, like here we're calling calculate from within main, there's a special area of memory in the Java virtual machine called the stack, and the stack is used for local variables and for remembering which method called which method, so we know where to return after the method is recalled. After the method is called, it's used for stuff like that. That's distinct from the heap, and the heap is an area of memory which is where objects are allocated when you use the new operator. So the stack is a relatively small area of memory that remembers function calls and local variables and stuff like that. And here we're getting a Stack Overflow error because we've called this function infinitely. We've called this within this. This calls this, which is this, and it's calling itself again. And it kind of goes round and round in an infinite recursive loop until we get this Stack Overflow error. So that's no good. But we can, this is legitimate if we provide some way of this method to stop calling itself at some point. So a problem with recursion, and a reason why it's not advisable to use it too much, is precisely the danger of Stack Overflow errors. If you call a method from within a method too many times, I don't know how many, I'm guessing tens of thousands, then you'll get a Stack Overflow error. And for that reason, it's better to avoid recursion. But there are some situations which we'll look at in which it's very, very useful to use a recursive method. So what we can do here is we could put an if in here, like say if, well, actually before I do that, let's do something slightly more interesting. Let's call calculate on value -1 instead. And what's going to happen now is, you see, we've got the same error again, unsurprisingly, but every time it printed out one less than the previous value until we got about 10,000 of them before we got down to -10,000 before getting the Stack Overflow error. So calculate initially has the value 4, which it displays, and then it calls calculate with the value -1, which is 3. So then we end up coming in here again, and the second time it prints 3, and so on. But now the interesting thing is it's possible to stop the recursion, because I can say something like if value equals 1, then, or maybe even it's, yeah, let's just do that actually. If value equals 1, then we can say return 1, like that. Oh, yeah, we're not returning anything at the moment. Let's just say return, like that. And then if we run that, now it prints 4, 3, 2, 1. So we're coming in fine, and it's calling calculate for values greater than 1, but when it gets to 1, it just returns. So we've got one method calling another method. What's this, four times, I suppose? Yeah, because we call calculate initially with 4, and we get this, and calculate calls itself 1, 2, I guess 3 times. Now we can do useful stuff with this, and one classic example is to calculate a factorial value. A factorial value is, if you take, for example, let's say example, e.g., the factorial of 4, which we write like this, 4 exclamation mark, that's not programming terminology or anything, that's some mathematics terminology. 4 factorial. I think you write it like that, or is it like this? I think it's like that. It doesn't matter anyway. 4 factorial is equal to 4 times 3 times 2 times 1, although the 1 obviously doesn't matter. So the factorial of any number is equal to the number multiplied by all the numbers below it, so to speak, leaving out 0, because if we multiplied it by 0 at the end, we'd just get 0, of course. And this is very useful in probability theory, for example. So this is called the factorial 4 in this case. So the factorial of any number is just this. Now we can calculate that using a recursive function, because what I can do is, here I can say, let's have a return value. Let's make this int. And here I'll say, if the value is 1, we'll stop by just returning 1. But otherwise, if the value is something greater than 1, we'll call calculate itself on value -1, but we'll multiply the return value of that by value itself, and we'll return this. This is getting a little bit more complicated now, and you'll have to think about this probably a little bit, unless you're cleverer than me, to get your head around it. Let's run. Excuse me. Let's run this again, and now what I can do is I can print out the return value actually here. So here, and let's run this, and now the factorial of 4 is 24, and I can I can also rename this to factorial, which might be handy, like this. So now we've got a function that calculates the factorial. I need to rename this as well, of any number passed to it, factorial 5 or whatever. And to see how this works, it's probably going to help if you just think through what it does for small values. So if we call this method here, I'm using like function and method interchangeably. It's a method because it's part of an object, but you could also call it a function or subroutine if you like. Subroutine programming lingo, function is more a mathematics lingo, but it's all good. So function takes in usually a number and returns a number. And let's say we pass in 1. What would happen is we'd come in here and it would say, is value 1? Yes, return 1. So this would display 1. So we pass in 1 here. We just get 1 like this. If we pass in 2, what happens is we come in here with the value 2. And it says, is the value 1? No, it's not. So it doesn't do this. It comes down here and it calls factorial on 1. In other words, 2 minus 1, which is 1, times 2. So we're taking 2 here and multiplying it by factorial 1. 2 times 1 is, of course, 2. And so that the factorial of 1 will just return here. We'll just get 1. So if we call it with 2, here it's 2. And doesn't execute that, it executes this. That's 2. This will end up being 1. So 2 times 1 is what is returned in the end from the function, and that's factorial 2 is 2. I don't know if that sounded hideously confusing or helpful, but either way, I'd advise just going through this logic for yourself. Imagine what this will do for the value 1 and then the value 2 and so on. I'm not sure what factorial 0 is actually. Probably it's defined as 0. We might want to think about how to define factorial 0, but this will do to illustrate recursion. And if we pass in 3, it's going to do 3 times 2 times 1. So we've got an extra step to it. It comes in here and it says, okay, 3 times whatever factorial 3 minus 1 is. In other words, factorial of 2. And then so it's coming in here a second time and saying, okay, we'll do 2 times whatever the factorial of 2 is. And all these values get stored basically on the stack, and the end result is you're calculating factorial 3. I think once you've got your head around what's going on when you pass in 1 and when you pass in 2, it starts to become fairly clear what will happen for 3 and 4 and 5 and so on, and you get the idea. You could spend days thinking about this until your understanding of it is as great as your understanding is of pulling out a chair from underneath the table, but it's probably not worth it to have that degree of clarity. You'll get the idea if you just look at a few small values of this. So this is a classic example of where you use recursion. The important thing to remember with recursion is always make sure that it's going to stop somewhere, and don't try to make it recurse thousands of times. Stick with small numbers, otherwise you could get a stack overflow error. Another classic example where we use recursion is, let's take a look, is if you look at the Towers of Hanoi puzzle, Towers of Hanoi, there's an explanation of this on Wikipedia, this simple game, which looks complex and intimidating at first, but it's actually relatively simple. The Towers of Hanoi puzzle is you have these discs on these rods, and you've got to move the discs by moving one disc at a time onto another rod, and you're not allowed to ever put a bigger disc on a smaller disc, and the puzzle is to move the entire stack to another rod, one disc at a time, obeying these rules. And if you look down here, somewhere we've got an explanation of the recursive solution. And although this looks a bit intimidating, it's actually in some ways easier to understand than calculating a factorial, I find. And where recursive algorithms really shine is if you can see what to do for one step of this puzzle, then you can use a recursive solution that applies that step over and over again. and solves the whole puzzle in a very elegant manner with surprisingly little code. It's better to use loops in general than recursion, but in this case using a loop would be actually quite hard to figure out mentally, whereas the recursive solution turns out to be pretty simple. You're kind of looking at the end result and saying, okay, what would I have to do to get to one step before that end result where all the tower has been moved, and write a method that does that, and then say, okay, we can use the same method to get to one step before the solution that's one step before the final step, if you see what I mean. If you can solve the second to last step, or I guess it will be the last step, then you can solve the second to last step in the same way, and the third to last step, and so on, just by using a recursive method. So if you want practice with recursive methods, try to calculate a factorial, and then I would say come to this Wikipedia page and see if you can implement a recursive solution for the Towers of Hanoi puzzle. Actually, that you'll also need some way of representing these disks using maybe a Java collection class or something. Or if that's too complicated, don't worry about it, because the most basic thing that you need to grasp first is just calculating a factorial or something like that. And when you can do that, you basically grasped recursion. So that's it for this tutorial.